All right, welcome to Chestnut Chat. Thank you all for joining us again. So I am Sarah Fitzsimmons. I am the Chief Conservation Officer with the American Chestnut Foundation. And we are, I think we're episode 53 or 54 now here on Chestnut Chat. So thank you all for coming. At a little bit of housekeeping before we get started with our guests and our main presentation. The only people who can share their screen or who can share their mic are me and the four other people here on the screen. So Mike, Jared, and John are our esteemed guests. Kendra and I are your regular hosts of Chestnut Chat here. So Kendra is our Q&A person extraordinaire. She will keep track of any questions that you have. So if you have a question, please use the Q&A module for that, and we'll do our best to answer those questions. Typically, I like to save those questions for us to have a conversation with our guests, but sometimes we'll answer those typing it in. If you have a chat and you just want to talk to one another, please put that in the chat. So Bruce says, seems the link they sent was for pre-registration. Yes, so our chats are now, we require pre-registration, and the main reason we do that is so that you get a calendar entry and reminders. All of that's automated. So if you kind of like get the link and you're like, I don't want to pre-register, this is annoying. Well, it's mainly so that it takes a lot of the reminders and that automation. Zoom takes care of all of that. So that's why we always send out the link for pre-registration rather than straight to the chat. So hopefully that works for the majority of people moving forward. I think that's pretty much it for the general housekeeping stuff. Today we're going to talk about hybridization. I'm going to show, Russell says it's Chestnut Chat 52, and as our frequent attendee and perfect attendance holder, Russell would, and plus he was one of our featured guests on episode 50, the episode 50 spectacular. Russell would know. I'm going to show a really quick presentation, then we're going to hop to John, go to Mike, and go to Jared and talk about breeding and hybridization of chestnuts that's taken place over the past basically 100 years. But I want to show a few things for
Sarah,
Yeah, sure, Mike.
before you do, did you start to record?
I did. And so
Okay.
what I do now is all of my meetings. So if you're on a Zoom meeting with me through my account, it records automatically. I will not go I won't repeat that mistake again. So I just start recording the second that it opens up. But I appreciate you bringing that up because I definitely don't want to have to repeat, and neither do you, the session again. So all right, let me share my screen here. Is that it? We'll just share. And I'll do this. So one of the main reasons I wanted to bring up the hybrid breeding during this session and at this timing here in September was because we have the symposium coming up in Connecticut, and we're focusing a large part of it at Connecticut Ag Experiment Station. And so John will be covering a little bit about the work, the results of some of that early breeding from the 30s, 40s, and 50s that had taken place at the Connecticut Ag Experiment Station, and trees that are now at Lesesne State Forest in Virginia. So I think that's going to be a really neat tie-in to wrap up this whole talk. But the main reason is to get everybody excited about seeing those trees in person. We have some fantastic talks. Peter Crane will open up our sessions on Friday evening. That's October 25th. And then Mark Ashton will close us out on the evening of Saturday, the 26th. And in between, we have a really great assortment of guests talking about, we have an educational roundtable, we have an eco-poet. So if you want to learn how to do poetry, I think that's going to be really fun. Stephen Tolowicki is going to talk about habitat suitability. Susanna Cario is the current steward of the chestnut program and Cryphonectria program there at Connecticut Ag Experiment Station. So we've got a really great program, and I hope you guys can come. So one of the main reasons to have this program is to talk about hybrids, talk about hybrid breeding, a lot of which started at the Connecticut Ag Experiment Station. So I hope you guys can come to the symposium and check that out in person. I'm going to show a couple of screens. We've showed this before. I was actually, last September was when we started talking about Darling 58 and some of the performance issues that we started seeing, and started talking a little bit about restoration being a process and not a product. And I think as we talk a little bit more about these programs and what the American Chestnut Foundation is doing. It led with the work that Jared's going to be talking about. You know, we talk more and more about the work is going to be a process and not a product, and this has been really the reality of chestnut work since the Connecticut Ag Experiment Station started bringing in chestnut importations from China and started breeding them all together. There's no singular recipe. There's no singular tree that will ultimately create the population of chestnuts that can restore ecosystem function back out on the landscape. And again, I am a broken record with this, but I mean, that really was the findings of this National Academy a publication that came out back in 2019 when they were looking at forest health and biotech and how those can come together. So, you know, another reason I like this program and the way we've got it set up is with John, Mike, and Jared talking about, you know, breeding that's been taking place since the 20s and still has relevance today. While we've tried other techniques, you know, mutational breeding, that still has a place. Hypovirulence is still being investigated and other ways of trying to work with the fungus. Traditional plant breeding is ongoing, as is genetic modification and other biotechniques. But the main goal is to have a main line of stability with resistance and diversity created through breeding. And so as a reminder, I'll re-show this slide as well. I want to thank Vasily and Jared for putting this one together of what is necessary to restore an American chestnut or restore ecosystem services back out into the landscape. We need sufficient heritable disease resistance, and I think Jared will really cover that from a quantifiable standpoint, and John and Mike will talk a lot about it, you know, what they're seeing in these different plots that have been out for decades now, and breeding in different ways. We need traits which perform ecosystem function of wild type American chestnut. And, you know, in the before times, that was mainly achieved through, well, the more American chestnut character, then the more of those types that we can put in. That was the whole background for the backcross breeding program, and also the thought behind the Darling programs, and some of the ongoing work with biotech, which is the more American it is, the more it's going to perform those functions. And so we'll talk a little bit about what's that balance, like how much American character do you need, and how much can you bring in from these other species within Castanea or these other techniques and still call it, how much can this tree still perform those functions in the landscape? And then finally, you need sufficient genetic diversity and adaptation for those trees to have the amount of resistance, to be able to showcase the amount of resistance and those ecosystem functions. So I think keep all of those three different elements in mind. That's really what we need for ultimate success. Today we're going to talk about all of the orchard locations that you see here. All of these are going to play a part in what Jared's going to talk about. John's going to focus on some work that is focused here near Charlottesville, Virginia at Lesesne State Forest. Mike is going to talk about Codorus State Park and work that's really focused here in South Central PA, as well as his plot up in North Central PA. So we'll get a nice little geographic look at work that's being done across the range of American chestnut. And with that, I'm going to repeat a plug again to come to the symposium in Connecticut. And so I'll put this link again in the chat for you guys to have. The other thing that I want to do, and I'll repeat it at the end of this program, is part of this work, what we've wanted to do with TACF is we get one of the most often questions we get. People call in daily at the office here in Pennsylvania, and definitely at TACF office, and probably John, you probably get this call too. When can I have an American chestnut? Can I have trees to plant? So we're doing the best we can to provide materials for everybody. I'm going to mention Hal Brindley again. Hal's the one who put together that gorgeous website for the symposium. He's also with our regional team in particular. Hal has created this great tool for you guys to go in and say, look, I have land, I want to plant chestnuts. What's the next step? So we've created a tool that we hope, it's in beta, so let's bang on it. Let us know what you think. We'll see how it works. You guys can be the first ones. Hal put it in there. Here it is, tacf.org/getchestnuts. Try that out, see what you think. Basically, it's a form. It's meant to get you through the process of is your land suitable? How many trees do you want to plant? How involved do you want to be? Do you like really want to get down and dirty in the research, or do you just kind of want to plant trees and walk away? It kind of leads you through that process, and we'll see how that works for everybody to get both the information you need and also more involved in the work that we do. One of the main reasons we want to do that now is after Jared's talk, we're going to have a need for sites to plant a lot of the material that we're creating now. And so we want to see how we can get more people involved. And this is more of the like very involved research aspects, planting trees, watching them for 10, 15, 20 more years, and helping us gauge how the resistance is being incorporated, as well as the phenotypes that we're looking for ecosystem function and performance. So with that, Kendra, is there any big Q&A that we need to take care of, or are we doing pretty good? I see a heart.
There's a couple things in there, but I think nothing that needs to be addressed before we get going, and there may actually be some more information to add to some of these questions, or yeah, I think I'd let them hang for now.
All right, well, let's get started. Thanks again, everybody, for coming. Looks like the chat's going well. Q&A is going good. John is he's the chair of our restoration committee for the American Chestnut Foundation, and also the president currently of the Virginia chapter, and retired from the Virginia Department of Forestry, and really involved in chestnuts for a long time. John, I'll let you add anything to that you'd like. Thank you so much for joining us and telling us about Lesesne State Forests et al.
Yeah, thank you, Sarah. I'll try and share. So, yeah, I want to try and briefly go over a long history of chestnut breeding at Lesesne State Forest that goes back to 1968. This forest was actually donated by private individuals to the Virginia Department of Forestry for the express purpose of chestnut breeding. And it's right in the real range of on the Blue Ridge Mountains, northern Blue Ridge Mountains. So there's lots of native chestnuts around, lots of chestnut trees we could use for breeding purposes. And it's at a pretty good elevation. It's adjacent to the George Washington Jefferson National Forest, just a couple miles from the Appalachian Trail. And over the years, there's been 3 main orchards put in: the hybrid orchard starting from the beginning of 1969, a backcross orchard starting in 88, and then the American orchard starting in 1980, but it actually tagged on to a irradiated program that was started in 69. So here's some drone imagery overlaid on some aerial photography. So we have the 11-acre orchard that was planted with trees from the Connecticut Ag Experiment Station primarily. It's about 11 acres, and this one up here is now a mature chestnut stand of 54 or so, 55 years old. We have the backcross orchards, these orchards down here, and then an American orchard, which is 7/10 of a mile away, so some distance to have some pollen separation. Not really the topic of this talk, but we also had another donation of a state forest near Galax, Virginia, also in this case, the southern Blue Ridge Mountains, a little higher elevation. And TACF put in a Nanking backcross orchard there. And then the backcross threes, most of the backcross threes, some of the backcross threes from the Virginia Department of Forestry program are planted in this Lesesne backcross orchard, but most of them are at the much smaller 2.5-acre orchard down at Matthews State Forest. So the history of the American orchard is a little complicated because when this was donated to forestry in 68, 69, there was Dick James from the Connecticut Ag Experiment Station was involved in setting up the hybrid orchard with my predecessor at Department of Forestry, Tom Deroff, but also Ralph Singleton and from the University of Virginia was working with irradiated chestnuts, looking for mutagenesis. And I actually just learned that recently that there were a total of 6,000 irradiated nuts planted in these 3 blocks of what was formerly a apple orchard. And I'll talk about the history of it, but that was basically a failure. But the root stocks of those irradiated nuts were used in 1980 to graft large surviving American trees onto those root stocks. So there's a one remnant chestnut in this lower block, and we've been looking for chestnuts up in here. We actually found some F1s up there, which I do not know how got there. So we're still trying to investigate that. So the genetic resources at Lesesne are can be looked at by population. We have the irradiated chestnut plantings, and really there may be a few sprouts from some of those trees, but generally they showed no resistance. Then we have the large group of Connecticut Ag Experiment hybrids planted over the year 68 to 76. And then we have grafted Americans planted on those irradiated root stocks from 1980-84. Lesesne State Forest was also the site of early hypovirulence work by Gary Griffin and Artman and a few others. And then about when I came to the Department of Forestry, right when I started, actually, they had started doing some pollinations with the LSAs from the American orchard with these hybrids, which are mostly F1s, at the Connecticut Ag Experiment from the Connecticut Ag Experiment Station planting there at Lesesne. And so the basis from 1990 to 2000 was 20 years of backcrossing using primarily those 2 sources, but also some wild LSAs found out and about in central Virginia. There was also continuing work by ACCF. Gary Griffins and Lucille started the ACCF program after this grafting, and they continued to do some more grafts and family plantings in the American orchard. But Department of Forestry continued on with B2 and B3 plantings, and then some LSA by LSA plantings. And then more recently, best by best and more LSA, and then even transgenic crosses were made over the last 3 or 4 years, I guess. And so a lot of people have been involved. So there's Al Dietz and Ralph Singleton with the irradiation program. Dick James, Tom Deeroff, Charles Burnham. I was actually glad to see in the old files that there was an active correspondence going on among the 3 of these about how to do the backcrossing at Lesesne. Deeroff, Artman, and George Dean worked on the grafted Americans. Gary Griffin and his students worked on hypovirulence. And then when I came on, worked with Tom Deeroff, got advice from Fred Hubbard, and then there was various folks, myself, Wayne Bowman, Billy Apperson, Jerry Creighton from the Department of Forestry. And then after I worked for forestry for 20 years, and when I moved on to another job, and then when I finally retired so that covers about a 15-year period where I worked on these programs as a volunteer coming from the Virginia chapter of the Chestnut Foundation. And we have actually Jerry Creighton retired, so the new manager is Zoe Bergman, who's very interested as well in the chestnut work there. Excuse me. So just to give you an idea, I mean, we have well in excess of 20,000 trees that have been planted or grafted there. There were at least 5,000. I'm thinking it's actually 6,000 nuts planted in irradiated orchard. Maybe none of those are left, or very few. The hybrids, over 11,000 were planted. There were 1,400 grafts made. And they're still about 15 to 20, depending on how alive you want, what your qualification for alive is. But there were 47 different sources that were grafted there. And then in 1980 through 97, Gary Lucille and others worked on hypovirulence on 3 of those graphs, the Thompson, Ragged Mountain, and Thoroughfare Gap trees. And that's published in a number of papers, and there's good, pretty important early work on hypovirulence. So from 1993, we did backcross 1s. From 2002 to 2010, Gary Lucille actually did more graphs and more family plantings at the American Orchard. Department of Forestry continued with help from volunteers from the Virginia chapter to do the B2 and B3 families, and then some LSA by LSA plantings. And then, in the last 4 years, we've worked on a lot of different things and a lot of genotyping and phenotyping. Excuse me. Sticky on this. Okay. Okay, one more. Okay, so 6,000 nuts planted, about 100 trees were actually transplanted from Dietz's West Virginia farm. The assessment in 1974 was that they were doing very poorly, and the transplanted seeds were doing very poorly, but the seeded trees were vigorous. But then some of the nuts they started producing nuts. Some were grown at the Augusta Forestry Center, our nursery in Virginia, and planted at a state forest. None of those seem to be surviving at this point. We haven't found any. But by 1980, they noted in the files that chestnut blight was severe, many trees killed back to the ground. And then in 1996, they measured and found that 95% of the sprout clusters, the largest stem, had been killed, presumably the grafts, but not necessarily. So moving on from there, sorry about my sensitive mouse here. Let's see. Okay, I also have a little delay. Okay, so getting to the Connecticut Ag Experiment Station. So these were the best trees selected by Dick Janes from the Connecticut Ag Experiment hybrid plantings, and some other sources found gathered from other planters around the country, really. And they 46 different seed sources. The greatest bunch of this were Chinese, Japanese, American complex hybrids. And then there was some just a smaller group, about 20% were Chinese American hybrids. And there were about 1,000 just pure Chinese. And then there was Sanguinii, some pure Americans, and some just Japanese American hybrids. They started selecting, Dick Janes and Tom Dieroff started selecting trees by pretty much subjective evaluation, looking at apical dominance and blight resistance. They did not do any inoculations. They just looked at the endemic blight population, which was plenty high. And in 1972, they selected 15 out of 1,000 candidate stems. And in 1975, they came back and ended up being able to evaluate 4,700 and selected 106. And then they came back in 1980 and looked just at those 106 that they had selected in 75 and came up with a selection of 36 of those that were still doing well in terms of blight resistance and apical dominance. And in 1981, they selected a final group of 8. These were just 6 seed sources. That was the woods lot group, which is probably several trees, actually, but we consider it one seed lot. The C13 and the number 40 Norfolk, which were all from the Connecticut Ag Experiment Station. And these were then decided to be used as the source of backcrossing. So there's a paper that is available. I can share it with you, that Dick and Tom wrote up and listed all the sources and their evaluation of those results. And as you see, there's actually 3 different trees from the woods lot tree that we have just considered to be the same source. And those generally are the nicest looking trees. Here's Tom Dieroff back in looking at the trees that are 11 years old and about 32-foot tall. So they grow well at Lesesne. So currently, these are 2 of the 8 original that were used in a fair amount of the crosses. So this one is row 38, tree 2. It's currently, well, this is measured a few years ago, actually, so it's a little bit bigger, but when measured at age 51, it's now 55. It was almost 18 inches in diameter and 72 foot in height. It's from Norfolk, and it is mostly Japanese by our genotyping. And we only have genotyping for 4 or so of these hybrid trees. So this is probably not representative of all of them, but maybe representative of the selections. I don't know. Then another hybrid is 3722. And is also about 18 inches, 17 inches in diameter, and 75 feet in height, also that age. And it came from Woods Lot, row 11, tree 8. I'd like to get this genotype to see if it's got a little bit more American in them, but it looks, it has nice timber form. Both of them do. They are tall. They've been competing at a tight spacing, and they have good blight resistance. But one thing we've noticed in this orchard is we've controlled competition over the years, and the biggest competitor, at least as a tree, is tulip poplar, and we've had to keep those. We've cut those out. Made a fairly good effort to keep them out of the stand, but they're still in there, and the ones we've left there for a long time are now 20 or so, 15, 20, maybe even 25 feet taller than the hybrid chestnuts. So that gives you some clue as to competitiveness of hybrids at least in the Appalachian Mountains, where historical records indicate that American chestnut would compete pretty well with tulip poplar up to a side index of 100, which is based on age 50, that you expect the trees to be 100 foot tall at age 50, and growing together, it implies that growing together American chestnuts and tulip poplar would be able to compete equally up to side index 100. But it does not seem to be the case for the hybrids. So a little bit more about the seed lots. The Woods Lot seed lot was open pollinated F2 seed from 3 mother trees in a Connecticut Experiment Station orchard. 3 culled 3rd generation selections of Chinese by Japanese by American hybrids. Burnham, back in one of the letters in the file, felt that these may include individuals homozygous for resistance from one or both sets of Japanese and Chinese ancestry. This family was consistently evaluated as having good timber form. Number C13 is actually not much is known. It came from Connecticut. It's open pollinated seed from a Chinese cross of unknown parentage. And number 40 Norfolk is also from Connecticut, I believe, and open pollinated seed from a Japanese American hybrid. So that's about what we know historically about their ancestry. And like I said, I like to get more genotyping to learn a little bit more. Oh, I'm clicking too fast. Hold on. Okay, back to where I need to be, I think. Sorry. It's the delay screwing me up here. Now I've lost the screen, I think. Okay, hold on. I'll try and go slow. Okay, the grafting large surviving trees. I'll go quickly through this to catch up some time. Mostly there were 31 sources and about 900 grafts made on 200 rootstocks. When the backcrossing finally started in '89, we had 10 surviving flowering grafts. now about 5, with only 2 thriving. Notably, Thompson and Ragged Mountain, which are shown here. Thompson is this double stem tree, and Ragged Mountain is the single stem tree over here. And they have been, because were inoculated with hypovirulence, these 2 trees, and including Thoroughfare Gap, which actually died about 8 or 10 years ago. But right now we have Thompson, Ragged Mountain doing very well, but we also have not doing as well Poor Farm and Loudon. And then the Amherst tree is in the wild still, in somebody's yard actually, or field, still surviving. But there was Thoroughfare Gap was a very good tree. It died possibly from Phytophthora. And we also have Loudon tree and Poor Farm trees still alive that we can get pollen and sometimes nuts from. But there's other trees that were involved in the breeding program that are not, some of these are still alive, some are alive in the sense that we have progeny of these trees, often from backcrosses. So the hypovirulence work, as I mentioned, was done just on Thompson, Ragged Mountain, Thoroughfare Gap. There's observations that have been published in the peer-reviewed literature about those observations, about their results up to 1999. This was that same 2-stem Thompson tree in 1999. And so one of the questions with Lesesne is how much that hypovirulence may have spread from these 3 trees to other trees in the American orchard, and possibly to the orchard 7/10 of a mile away. We don't know the answer to that, but we would like to look into that, see if we can detect hypovirulence in either orchard. And here are some results of that Thompson, Ragged Mountain, and Thoroughfare Gap results from Gary and others, Artman's paper. So since that work with Connecticut Ag Experiment Station, we used the backcross 1 full sib families. We made 275 families, 160 used woods lot as a resistance source, 104 as C13, and number 40 Norfolk, only in 11. And as you expect, actually the best ones come from these top 2, which may just because they were more prevalent, but that seems to be the case. So backcross 2, we still have woods lot C13 and a fair number of number 40 Norfolk represented. And the backcross 3, I do not have those full data yet. But we started in 2021, I think, was the first year we started doing genotyping and phenotyping by the methods that Jared and TACF has developed. And here are the results of different sources. So the backcross 1 are our generations. Backcross 1 generation has 137 blight 1s by the stem crown selection, 48 blight 2s, and so on. And backcross 2 with smaller number total, but still a fair number of 98 blight 1s. The LSA by LSAs, and I'll mention that some of these, and I'll show you shortly, some of these LSAs are actually were mistakes. We thought we were crossing backcross trees or hybrid trees to Americans, and the pollen contamination, apparently American pollen got in, and so some of these supposedly controlled crosses actually turned out to be American by American crosses. And of those, not very many of them, but we do have that have been evaluated. We have 1 that's a blight 1, 14 that are blight 2s. And then we have some other trees which were not classified as LSAs, but it may very well be that when they were crossed, we ended up with 1 blight 1 and 1 and 2 blight 2s. And then the hybrids, we don't have many evaluated, and really only 3, and they show up as blight 2, 2 blight 1s, and 1 blight 2. So some resources to continue breeding work anyway. Let's see. So here's a picture.
Hey, John, before you get too far, I've got a couple questions about Blight 1 and Blight 2 and
Yes.
what that means. And I think Jared may discuss that a little bit more in depth, but do you wanna talk about that just before we leave that too quickly?
Yeah, so that's a combined, and maybe Jared could correct me, but that's a combination of the phenotypic evaluation of blight resistance and crown form, and the genetic prediction from the genomic model. If both those things are high enough, they get to be blight 1, and if they're not quite high, they're blight 2, and then so on down to not blight resistance or back. Is that a fair assessment for now?
Yeah, like the blight 1s, if the Chinese is the average resistance is 100 on that index, and an average resistance of American is 0, the blight 1s have resistance greater than 40 on that. So anything above 40 is a blight 1.
Gotcha. Thank you. So here are pictures of some trees. This is 2-2, and it was supposed to be Woods Lot tree by Amherst tree. I found something in the records. We weren't apparently always consistent. It would have to have been the Amherst tree as the mother, and supposedly the Woods Lot tree as the father, because when we had this one genotyped, it came out 100% American. And so it was an outcross. It was not the intended control cross. But nevertheless, it's at age 24, which is like 2 or 3 years ago, it was 16-inch diameter and 60 foot in height. And I think, I don't remember, I believe this is one of the blight 2, but I'm not sure on that one. We also have a LSA by LSA cross, which is Ragged Mountain, one of the trees with hypovirulence introduced, maybe still there, that was crossed with a wild LSA Higgins tree, and it's now at age 24, 50 feet tall, 12-inch diameter. It's 100% dentata by genotyping. Blight 2 by stem and crown. Blight 1 by stem, crown, and size index, which is a little more complications to that definition. And Jared could probably do a better job of describing this as well. Where the growth, the total size of the tree is added into evaluation. So I think the more vigorous, fast-growing trees do better. And so this tree is actually one of my favorite trees for a number of reasons. Obviously, it's doing well in terms of blight. It's doing very well in terms of growth. It's just a very vigorous, and it's also a very fecund tree. It produces a lot of burrs. It's easy to pollinate. It's just a vigorous tree. One thing that actually made me wonder before we had it genotyped is that the burrs and nuts are kind of on the large size for Americans. But it's been genotyped as 100% American. I often wondered if it had a little European in it, but that has not been indicated in the genotype. One more, and then I'll wrap it up. So we also have at Lesesne a problem. This is actually a few rows of open pollinated Americans that were planted in the backcross orchard, kind of as not necessarily as controls, but just because we had them and we wanted to see how they would do. And they actually grew very well and seemed to be reasonably blight resistant. And then about 5 years ago, they were inadvertently planted in a little bit of a low drainage spot of the orchard, which is generally pretty well drained, but enough that we had a culvert in the road right above it. So we think this was a little wetter site, and these trees started dying quickly with Phytophthora symptoms, and we tested and we found we had Phytophthora in there. So These were actually then harvested, and I've got a stack of lumber in our shed there at Lesesne from these trees, and some of it's already gone to other uses, but we still have some available. But they grew very nice. We were very hopeful for them. There's still a few of them alive, but they appear mostly to have died. They may have died. Some of the earlier planting, some of their trees when they were first planted probably died from blight, but we had pretty good survival in these rows, and they didn't really get hit until they started showing Phytophthora symptoms. So, which, you know, makes Lesesne a little less valuable because there's Phytophthora there. So we always have to consider that in what we plant there and how we evaluate things. So that's a lot very quickly, but I think the time hitting it about right. So I'd like to thank the Department of Forestry. I worked there for 20 years and then 15 years as a volunteer. And then over the years, we've had a lot of good advice from different folks. And I could make this list a lot longer, but I think that wraps it up for me. Sarah, if you want.
Yeah, John, thank you so much. I really appreciate you. That is a lot of material. And one thing I know there's a lot of interest in LSAs, and Frank Skalak. Frank, good to see you on here. Thanks for your questions about Americans and what we're doing. I think, Frank, for your questions, I think we'll be able to get a lot more in depth with what Jared's going to talk about. I hope to have a whole other session early in 2025 about American chestnut breeding and LSAs. I want to really hone in on that and focus on that because there is a lot of interest in. If you guys follow Facebook, there's our Indiana chapter president, Bill Dieter. He likes to call them resilient Americans, and talk a little bit more about what resistance is there. Jared will talk a little bit about it, but we've only cracked the surface with what's out there for Americans. So I want to talk about that a little bit more in depth. John, two people on your slide here, Sandy Anagnostakis and Dick Janes, they will be at our symposium in Connecticut. And so I think if you guys want to see, you know, some of the progenitors of all of this material, I really hope you guys can come to Connecticut and hear from the people who made some of this early material. And they'll tour us around the session. If you want to get it straight from Sandy, come to the morning tour at Lockwood during our symposium. She's only going to be able to make the morning session, and then she's got to go back to Massachusetts where she is these days.
Sarah, I would add too that actually the LSA plantings at Connecticut actually have Thompson, Ragged Mountain, and I think Loudon planted there. Yes.
Yeah.
And
Okay.
and they're, you know, among the better ones there. So, you know, and yeah, there's good evidence that the progeny or grafts from those trees do well.
Excellent. Well, another reason to come to Connecticut. So thanks, John. I think now we'll turn it over to Mike. Mike Aucott has been working with the Pennsylvania, New Jersey chapter for a long time, and he's taken over a program that he's going to describe called the F1, F2, F3 timber program that was started by the chapter about 20 years ago. Mike, I'll let you take it away. I mean, I know you're still teaching, right? To some degree, is that right?
No, I've
No?
retired from that, but I came out of retirement. I worked for New Jersey DEP again as a consultant.
That's what it is.
on
Okay.
Climate issues. Yeah.
Yeah. Well, Mike, it's a pleasure to have you, and thanks for joining us, and take it away.
Thank you, Sarah, and thank you all. It's great to have an opportunity to share a little bit about what I've been up to, and the other people on the F1, F2, F3 have been up to. I'm going to try to share my screen here. See how this goes.
Hey, Mike, how about this? Can you email me your presentation?
Sure.
We'll go to Jared.
All
You
right.
email me your presentation, and then I'll share it. Maybe we can get rid of the black box.
Okay.
Jared,
Okay.
I know you might have thought you had time to eat lunch or whatever. Are you prepared to go on now?
Yeah, I can go on.
Okay,
All
all right.
So I'm going to talk today about optimizing the breeding and kind of rebooting some of the breeding program with hybrids using genomic tools to help us improve resistance while selecting for majority American chestnut ancestry. So why are we continuing with breeding? It looks like a large gains in blight and Phytophthora root rot resistance are possible if we do this optimized breeding and selection program. Traditional breeding is not regulated compared to biotech. That seems to be a major bottleneck in getting trees out, is having this regulation. So all of us can participate in this breeding program. And the American Chestnut Hybrid Program represents genetic diversity from across the range. We've had a lot of volunteers over the years find wild trees and breed hybrids with these wild trees to capture genetic diversity. So we've represented, well represented the native diversity in our breeding program through all chapters. So this is something that we had a science review recently, and Fikret Isik, who's on this Chestnut Chat as a attendee, showed this slide of breeding works. We know in other systems, it is the most reliable method to improve traits that are complex, that are controlled by many genes. In this case, chickens here have been bred from, and their size has tripled from 1957 to 2005. This wasn't done through knowing the individual genes that are involved, but rather selecting for improved growth over multiple generations. And that's continued to accelerate and improve through genomic tools to select, to improve the selection and speed it up. So with hybrids, with American chestnut and Chinese chestnut hybrids, the central challenge is we want to capture enough disease resistance from Chinese chestnut for long-term survival. And here, this is a picture of the mahogany tree at the Connecticut Ag Experiment Station. This tree was planted in the 1930s. It's been living with blight, you know, for that entire time, but it's probably about 50 feet tall. And this is a photo from Anna Sproul, who's on this call, who's a member of TACF and a board member, who took a picture of maybe the largest American chestnut in the world in Belgium, in an arboretum. And this tree was planted in 1902 before the blight. And so it's over 120 years old now, and it's probably over 100 feet tall. So you can see that the American chestnut has this great growth potential when it doesn't have blight. So we need to be able to capture that competitiveness. So that, to me, is we need to probably be selecting for a majority American chestnut ancestry while also selecting for this resistance. So how have we gone about selecting for resistance over the long term? We've gone through 100, maybe over 100 orchards now from all the chapters, Meadowview, Lesesne, and we've looked at a number of traits like whether the main stem is alive, whether the trees have large cankers, sunken cankers, canopy dead, exposed wood, sporulation, sprouts. These are all signs of susceptibility. And many trees might have one or more of these kind of signs. And, you know, each tree is like a snowflake, you know, they each have like a little bit of different of a phenotype, but together we're capturing something by combining these traits into a blight resistance index, which I scaled from 0 being the average American chestnut resistance to 100 being the average of Chinese. So you can see that there are some trees that have majority American chestnut ancestry and you know, intermediate resistance greater than 40. So those are the blight ones that John was referring to. And these trees, you know, what that indicates to me is that we could probably, through additional generations of selection, continue to improve that resistance while maintaining majority American chestnut ancestry. So here's kind of some examples of what these trees look like. And a lot of these orchards, there may be like one tree that looks beautiful like this in the orchard. And so they're spread out all over the place, and they're often pollinated by less resistant neighbors. So we need to, our challenge is to be able to breed these trees over, you know, this wide geographic area, and then bring their progeny into centralized breeding locations that we can continue to improve the resistance. But I just wanted to show you that, you know, breeding has worked in terms of improving the resistance and retaining majority American chestnut ancestry. We do have examples of these trees all over the place. So how much blight resistance do we need? And one of the ways that I've been looking at is like, there are a few trees in our, you know, we've phenotyped many trees, and a lot of these trees are over 15 years old. They've been inoculated with Cryphonectria, the chestnut blight fungus, and they've had main survival. The main stem is surviving, no exposed wood, no cankers that are swollen or cankers that are only swollen or flat, no sporulation, no stump sprouts. Canopy is 90% alive. So I asked, what is on my, this resistance index, what is the average blight resistance of these trees? And that resistance is 65. So this is a picture of Bruce Levine, one of our board members at Lesesne State Forest with some of these F1 hybrids at Lesesne. These trees have been alive for at least 50 years and surviving with chestnut blight. So can we get trees that have that level of resistance, but more American chestnut ancestry? That's the challenge. So chestnut blight is not the only impediment. We also have to contend with Phytophthora root rot caused by soil-borne pathogen, Phytophthora cinnamomi. And it's predicted this pathogen is limited in its range to the southern United States, but as climate warms and the winters are getting warmer, it's able to spread and infect trees further north. So having some of this resistance is an important factor. Maybe we don't have to have trees that all of our trees have resistance to this pathogen, but a subset of the population should also have resistance to Phytophthora. And for the last, from 2005 to the current times, we've been working with Clemson University, the U.S. Forest Service, Joe James, one of our volunteers in South Carolina, to basically, we want to evaluate our trees' resistance to Phytophthora. We don't do that by giving them the disease in the field. We don't want to spread this pathogen all around. What we do is we take the seeds from our backcross trees, we bring them into a greenhouse, we plant them in a greenhouse, and we give them the disease. And we see how do their progeny of these trees survive. And ones with resistance, obviously they're transmitting that resistance to their progeny. That's a slow process. We've screened maybe 900 families over the last, almost 20 years now. So we've also been doing genomic, testing on trees and being able to predict the resistance of the trees that we haven't yet screened. And again, we're seeing trees with majority American chestnut ancestry and intermediate levels of Phytophthora resistance. So again, this seems to be that not all the genes contribute to these traits, and we can select for majority American chestnut ancestry. So how are we going to do this going forward? We want to select parents that meet some minimum standard for blight and Phytophthora resistance and American chestnut ancestry. And so in this first generation, on average, we're selecting for parents that have resistance greater than 40. They have American chestnut ancestry greater than 70. And we're collecting pollen from these potential parents. We're freezing it. And then when the trees are ready, we're going to pollinate our best, mothers with that pollen. And then we're harvesting the seed and growing the seedlings out in a greenhouse, taking little leaf clippings and sending them off to get genotyped, where we can select for even greater resistance of the progeny. And then we select better kids that have, resistance greater than their parents. So we're selecting 10% of the best to plant into seed orchards. And we're doing this, and we're capturing diversity from the chapters through this program. So we're regionalizing it. So the chapters are combining forces. And the people from the north, like Pennsylvania north, there's a lot of good trees, including some of Mike's and Codorus State Park that we're using for this program. But we're also breeding with the rest of the chapters programs to capture that diversity. This is a map from Alex Sandercock, who has done a lot of whole genome sequencing on American chestnuts and divided up the range into 3 different seed zones based on how the DNA is related to climate. And we see that the most genetically distinct population is in the southern part of the range. But the central and northern part of the range is also important for climate, for cold adaptation and things like that. So yeah, but where our priority in doing additional germplasm conservation is collecting from that southern part of the range. So we've also worked with this company in Australia called Diversity Arrays Technology to develop cost-effective genotyping we can basically look at the ancestry, the Chinese versus American versus Japanese, European, whatever species we have in hybrids. We're able to look at ancestry across the genome. We're able to predict the disease resistance from the DNA sequencing. We're able to look at climate adaptation through that. And then we also have some markers that for like the Darling trees and the Darwin trees, where we can look at OXO inheritance. So this is costs about $18 a tree to do the genotyping, just the cost from the company, and then we also do some analysis downstream from that. So it's fairly cost effective, but we need to be able to send samples from like hundreds of trees at a time. So it's not like you can just send a one-off. If you want to get a tree genotyped, you have to send us those samples, and we'll include them in with the rest of the samples that we're genotyping. So how does genomic prediction work for disease resistance? Basically, what we're doing with genomic prediction is we are taking each tree's resistance is basically its own phenotype plus a weighted average of all of its relatives' phenotypes. So it's like we're judging your genetic merit, let's say your height and the height of all of your cousins, nephews, aunts and uncles, parents, grandparents. We're looking at all of that, and we are taking a weighted average of, let's say, your height and all of your relatives, and saying that is your genetic potential for height growth. With genomic prediction, we maybe not, we're just looking at the seedlings. We're not actually looking at the resistance by inoculation, but we're looking at all of the relatives of that tree's resistance, and we're predicting based on the relatives how these trees are going to perform. So that genotyping gives us a very good idea of the relationships, and it enables us to predict the resistance without having to inoculate every tree. So we can use that to speed up the process. To make gains, we need to go through multiple generations of selection to improve the resistance. And so one of the things I was just at a conference last week, and one of our collaborators, Tom Clack, has gotten very good at growing trees in a lab with a high light, fertile, and ample fertilizer in big pots. And basically he can grow trees, taller than 7 feet tall in 1 to 2 years, and he's able to produce seed from those trees. So that's one way that we can possibly, speed up this process a bit, is for some of the trees, we can, select the best progeny from our Best by Best program, and then grow those in a light setting, high light setting, and get seeds from those and iterate through this process of genotyping and selection to improve the resistance. So I did some simulations looking at 4 different potential breeding tracks. And what I did is basically I used the genomic prediction, the current generation of phenotypes, to predict the resistance in the future generations, from the current up to 3 generations forward. And basically I looked at a breeding track to just maximize blight resistance, a breeding track to maximize Phytophthora resistance only, a track to maximize blight and Phytophthora simultaneously, and then a track to maximize blight resistance in large surviving American chestnuts. And each of these tracks, I was selecting for trees that had at least 70% American chestnut ancestry. Obviously, with the large surviving trees, they have 100%. And so basically, how many generations, I wanted to know how many generations will it take to get us to that level of resistance of 65 on that 0 to 100 scale. And if we just select for blight resistance, we can get there in 2 generations from current. So do 1 generation of Best by Best, maybe do some of the speed breeding, but also plan out seed orchards with that material, and then select the best parents, cross those parents together, and plan out that 2nd generation. And that 2nd generation, I'm expecting us to surpass that minimum level of resistance that we need with trees that have greater than 75%, or like on average about 75% American chestnut ancestry. But like overall 70 to 80% variation in American chestnut ancestry. With Phytophthora, similar story. We can get there even in we can get there about 1 generation of breeding, and it really improve the resistance more than we probably need in 2 generations. And with the LSA program, it looks like the level of resistance that we're going to get will improve, but it looks like we're going to still be below that threshold that we need. And I think that, there's more work to be done on looking at that heritable resistance and how these trees, how the competitive ability of the trees also factors into how well they survive. So I think it's still important for this to be a component of the breeding program, But in terms of our efforts, I would say about 50% of our efforts is in this best blight, selecting for maximizing blight resistance. Maybe 20 to 30% is balancing blight and Phytophthora resistance. Maybe 10% is in the Phytophthora only breeding program and 10% in LSAs. So that's kind of how I'm envisioning, spending our efforts going forward. So we're genotyping, we're the next few years are going to be doing these crosses and genotyping a lot of trees. So I'm envisioning that, 10% of the best stuff can go out into seed orchards. That's going to be grown up for the next, 10 to 20 years to produce a lot of unpollinated seed. Maybe 10 to 20% can also be put into small stem assays. That's looking at the early, getting an early look at, are we achieving what we had hoped in terms of blight resistance? So we can evaluate, how the trees are doing by inoculating the seedlings in their first year. A lot of the material can go out into field trials. That doesn't get, it's not the 10% best, but there's still a lot of material that will be good. And I think that we can continue to improve the genomic prediction models by putting them out into field trials across the eastern US, inoculating that material. It's been genotyped, and we can get really good predictions based on the looking at the relationships between the genotypes of the trees and the resistance. And of course, we want to continue to improve Phytophthora resistance so that some of that material can get inoculated with Phytophthora cinnamomum. So this is where, the chapters come in. This is where people want to say, we want to plant chestnuts. And one of the things that we are thinking about is planting about 20 to 30 sites across the US of genotyped material. We're thinking each site would have about 300 trees. So with that about 7 by 15 foot spacing, that's about an acre of land. And that material would get inoculated and evaluated over the long term. Some of the material can get planted out in forest trials as well. So we're going to have a lot of this material from our Best by Best breeding program. And we'd like to plant out a network of trials to look at, evaluate resistance over the long term and evaluate, local adaptation with trees from different parts of the range planted all across the native range of American chestnut. So that's a call to action, is to participate in this program of looking at these trees over the long term and helping us to improve the genomic prediction models. So yeah, the last thing is, as we surpass, I expect we're going to be surpassing our minimum resistance thresholds, but are we going to be generating trees with sufficient competitive ability to, grow and compete in the eastern forests? And one of the things that we're doing is working with Virginia Tech scientists to do some remote sensing on, these are trees at Lesesne. If we can develop ways of looking at the architecture of the trees and the maximum height growth and using genomic prediction to select for these traits as well as select for resistance in future generations, we can improve all of these traits simultaneously. So that's going forward, we're going to be incorporating more forest competitiveness, but I think that first, our goal is to get enough resistance for the trees to survive. So with that, I'll conclude and say thank you to all the TACF staff and volunteers who have helped with the breeding and phenotyping going to these orchard locations. That was a huge effort. We worked a lot with Jason Holliday at Virginia Tech, who did a lot of the genotyping. We worked with Forest Service for Phytophthora screening and Steve Jeffers at Clemson. We have some reference genomes, very nice, working with Hudson Alpha in Alabama to generate those. And then we've gotten a lot of philanthropic funding to support this work over the years. So hopefully that will continue, and we can, this program, I feel hope that we will get there with using these advanced tools with the genotyping to select for the resistance and competitive ability simultaneously.
Jared, great stuff. I think I hope Hal's still on here, and he might relink his tool so that survey that Hal's put together to see if folks want to be a little bit more involved in the program that Jared just described. If we can find sites that help us with that. I have one question that I want to give to you, Jared, and then Mike, I got your PowerPoint. I'll show that here in a minute. Jared, Anita asked, what do you do about linkage drag?
Yeah, linkage drag refers to you're going to be, as you're selecting for resistance, like a gene for resistance, you're going to be selecting for the surrounding parts of the genome as well. And so you'll be dragging along Chinese genes that have nothing to do with the resistance, basically. And so the way to deal with that is to go through multiple generations of selecting for majority American chestnut ancestry and improved resistance. And each generation, you're going to get like a recombination between the Chinese and the American genome, and you're going to be selecting for parts of the genome that are more American where we want them, and where that they don't contribute to resistance. You know, the parts of the chestnut genome that doesn't contribute to resistance, we want to make American. And the parts of the genome that contribute to resistance, we want to make Chinese, basically. So we want to select for more of the Chinese genes that contribute to resistance. And for the rest of the genome, we want to select for American chestnut ancestry. And, you know, it's kind of hard to determine what percentage of the genome contributes, but it's probably on the order of 20 to 30% of the genome that's contributing to resistance. So we want to get that best 20%, you know, from the Chinese, and then the rest of it's American. But that's done through multiple generations of breeding and selection.
Thanks, Jared. I appreciate you answering that at the end. All right, Mike, let's see if we can make this work this direction. And if we get the gray boxes.
Yeah, and we're just going to go through pretty quick. We don't have a lot of time here, so just keep moving. We had talked about how Dave and Bob had hand pollinated, and here's the Codorus F1s. The Codorus F2s would be the next slide, and there we go. And this orchard now has been culled down quite a bit. I think there are about 44 of these left, and Blake Grabowski, who's now the North Central Regional Science Coordinator, has collected pollen from some of these that remain. And I think today, they're actually harvesting nuts from some of the trees that Jared has indicated and that look to be the best trees. Let's keep moving. Dave recruited in 2012. He stood up at a meeting and said, anybody want to plant some chestnuts? I raised my hand, and a bunch of other people did. And he recruited some of us to plant F2 nuts, similar to what we just saw at Codorus, at other locations. And this became the F1, F2, F3 program. And Lake and I have been visiting these, and we have some more to visit this year. And we'll see what happens. Some of the orchards are being well maintained and have some good looking trees. A lot of the trees are not good looking, and I'll talk some more about that. Dave and Bob also pollinated a surviving American hybrid near the Harrisburg area, and that's the Kelly tree. We can keep moving here. And here's what the Kelly tree looks like today. It suffered some dieback. It's apparently got about 12% sativa, the European chestnut. And Dave always referred to it as an American hybrid. It's mostly American. And that was pollinated with pollen from the Amherst tree. And this is a fairly recent picture of this tree. And there's another one coming up here, another picture. Next slide. This is Fred Hebbard with the Amherst tree. You can see it's a big tree. And as John has mentioned, it's surviving yet. So it's got some resistance. Then they took the nuts from the Kelly tree and they planted a bunch of them at Codorus. And Dave had, before his death, was distributing thousands of these. We can keep going here. This is what it looks like last couple years ago. And these trees are growing nicely for the most part. This orchard has been culled. A lot of them have not grown so well, but the ones that remain looking pretty good. And you can see they do show some cankers, but they seem to be healing for the most part, the ones that remain. So let's keep going. Another picture of relatively healing cankers. Now we'll go back to Bob Leffel in the 1-2-3 program here. He argued that timber suitability is what we want, that it doesn't really matter so much about how pure the ancestry is as far as dentata is concerned. what we want is timber suitability. And he felt that if we had trees that had a large percentage of Asian, we'd get also resistance to Asian gall wasp, Phytophthora, and other afflictions. Keep on moving. Next one. So here's Bob, and I remember very well, he came sort of barged up on stage at a meeting of the growers a few years back and started talking about his ideas in the F1, F2, F3 program. And he said, well, we went to timber producers in Pennsylvania and we asked them, what do you want in a tree? And they said, well, we want a tree that can produce 2 or 3 16-foot lengths of timber, blight resistant, can survive in the forest, reproduce in the forest. And they didn't say anything about whether the leaves were canoe-shaped or rowboat-shaped, or whether the twigs were greenish or reddish, or whether there were little hairs on the underside of the leaves. They didn't say anything about that. So that was kind of Bob's view of what we needed. Let's keep on going here. And I think, as Jared has pointed out, and we've seen, there's certainly a rationale for keeping a significant percentage of it dentata in a restoration tree, because it needs to fill the ecological niche, and we don't really know how much dentata you need to confer key attributes. Keep on going. Next one. And so, nevertheless, the F1, F2, 3, although when it was established, we thought there were only 3 genes involved in blight resistance. We know that there's more than that. As Jared had pointed out, a lot of the genome is involved with blight resistance. But nevertheless, the way the F1, F2, F3 program has played out, there's a large segregation of genes, and it's yielding important data on the genetics that are behind blight resistance, growth habit, and other traits. Let's keep going. And they're a motley crew. And I'm going to talk mostly about my orchard, and it's a small sample compared to the vast number of trees in Lesesne and that Jared has been working with. But nevertheless, I think it gives an example of some of the things that are worth looking at. And I do have a bunch of Americans in my orchard, so these are valuable controls. A lot of those are Kelly Amherst, but not all of them. Let's keep on going here. My orchard is in northern PA. It's a much shorter growing season up there than a lot of the chestnuts range. It's cold. It's high elevation. It's about 2,200 feet, and but there are native chestnuts in the area, and so it's a place where we can look for regional adaptation qualities. Let's keep on here. When Dave asked me to carry on the F1, 2, 3, he said, Mike, it's going to be the good and the bad and the ugly out there. And there's some pictures from my orchard that illustrate the good, bad, and the ugly. Let's keep going here. Next one. And this is an orchard, a couple of the plantings from a distance. We'll just go through these pretty quickly, Sarah, one after another, that you can see there's some variation. Here's a 7-year-old hybrid, a 9-year-old hybrid that doesn't look so good. Onward. This is a 9-year-old hybrid that just won't grow. I keep these trees because I think a lot of them have blight, and we want to have a lot of blight presence in the orchard. Onward. Another old hybrid just isn't going to grow. This tree is not going to reach the canopy. Let's keep on going. And I think we can run through these pretty quickly, Sarah, just one after another. Thanks for doing this. And these are hybrids that are turning into shrubs. They've been blighted. The main stem is dead, but there are some that look pretty good. This is one of them. And there's a couple more we'll come to. The arrows point to a Kelly Amherst on the left and a hybrid on the right that I think is mostly Japanese, but I'm not sure. Let's keep going. This is the Kelly Amherst, 12 years old. It's about 27 feet tall, and I think for that part of the state, that's good. I think it's good growth. And there's a comparable one. Next slide. This is the next slide is a Japanese hybrid, I think. And I'm hoping we can get some genotyping on these, because that's what we need to really know. Keep going. I'm seeing a wide variation in a number of traits, certainly in blight resistance, and we can go through these quite quickly. Just one after another. This one is cold resistance. The hybrids do not hold up well to the cold snaps that are common in this part of the country. They get burned back. Potato leafhopper. That used to be a potato field where my field trees are, and the potato leafhoppers optimistically show up every spring looking for potatoes, but they find chestnuts and they feed on them. Next one, next slide would be good. And this is the kind of damage they do. You can see the first growth, not so much. Middle growth, where the leafhoppers had arrived, the leaves are stunted and twisted, and then later on, after the leafhopper population dies down, the trees grow unafflicted again. The Americans seem much more resistant, interestingly, and it's not surprising maybe because the leafhopper is a North American insect. Chinese trees and the hybrids don't like the leafhoppers. Next one. And I think there's not a lot of variation in another important trait, which is the ability to feed leaf-eating insects. Let's keep going. More work on that is needed. And the real thing I'm interested in, and it harks back to what John was talking about, and Jared also, the ability to compete with North American trees in the forest. And what about variation in rapid timber type growth? Let's keep on going. And there's a couple things to consider here, really three. Blight resistance evolved over probably millions of years. But I think that possibly, and this we go to the next slide, I think here, possibly orchard type growth characteristics may have been deliberate. It's not clear to me. I think we need to take a close look at this. And if it was deliberate to breed trees that have orchard type growth, it might be possible to reverse that fairly easily with breeding. Next slide. And so if it's due to only a few genes, we might be able to pull that back with selective breeding. Next one. I think I see evidence that some F2 hybrids do have fast timber type growth. And I want to show a couple distributions in the next couple slides. This is measured the growth rate of my dentata trees. And this past year, they on average grew about 2.5 feet. This is a normal distribution. Some grew a lot more, some less. These are trees that are 4 years old or older. Next slide. And this is what I see with the hybrids. Their growth rate is significantly slower. This is a statistically valid finding, but there are some that rival the North America, the dentata in growth. And the real question to me is, and we can go to the next slide here, whether Bob's idea is right, that we could breed a timber type 50% or greater Asian hybrid, or let's keep going, whether these few hybrids that seem to be fast growing perhaps have significant dentata ancestry. And I'm optimistic that genotyping is going to tell us more about that. Next slide. Because we do see among the F2s at Codorus a distribution that looks normal they average 50% Asian, but some have mostly American, some have mostly Asian ancestry. So it's possible that my fast-growing hybrids are mostly American. Maybe, however, they're mostly or largely Asian and are reverting to this perhaps ancient tall timber type growth. Next slide. And that's the question here. You know, what do we see with this? And I think I'm going to wind it up here. Thanks for the opportunity to share this little bit. I hope we have a little bit of time for some questions.
Thanks, Mike. We're right under the gun. We're right before 1 o'clock, which is when we normally cut off. So thanks for going through that. I know some folks have already had to take off. I'm happy to stick around and answer a few questions. Fikret says, good stuff. So Fikret, thanks for joining us from NC State. Recurrent genomic selection is an effective method for increasing the frequency of favorable genes across multiple traits. So that's a nice plug there. Let's see what kind of questions we have. Actually, not a ton. Let's see. John Himple says, Jared, do you anticipate that at some point with the Best by Best trees, that the next step will likely be to go on and replace various Chinese genes with that are linkage dragged along with genes that contribute to resistance?
Yeah, I mean that would be done through recombination, not necessarily through like editing the genome. So yeah, I think that we can just go forward with recombination to select for majority American chestnut ancestry. And the other thing I've been thinking about is like, we need to just get trees to the point where they can live and they can reproduce. That's a tall order, but like natural selection will start to carry out further improvements going forward. So whether or not 70% ancestry is good enough, we're going to have like trees like Mike showed where they're going to vary a lot. And so we need to get a population that has the ability for some of the trees to survive and natural selection will take over. So it's not like we need to have perfection. And, it's often natural hybrid zones, you get recurrent selection back towards whatever parent, like maybe American chestnut ancestry is really important, but over time, we're capturing with that, if those Chinese genes are contributing a lot to survival, we're going to capture the most important stuff through natural selection, hopefully carrying on the work.
Thanks, Jared. One more question. Bruce asks, have you genotyped the fast-growing F2s to see if they have much Asian in them?
Well, I don't know who's that's to. That certainly hasn't been done with mine, and I'm very optimistic to see what genotyping will reveal.
Yeah, I think. Oh, sorry.
Well, yeah, we're planning on doing it next year. So yeah, there's Mike, you have like 15 to 20 of these really good trees. I would definitely genotype those. And if we have funding, we can do some of the other ones that are not so good.
Let's see. I got a bunch of people putting questions in the chat, and it's hard to keep up with this. So please put them in the Q&A. Let's see. I'll try to do my best. Gail had a nice comment. Thank you, Gail. Thank you so much, John, Jared, and Mike. Great summary of 100 years of chestnut breeding and efforts by many. There is hope, and yeah, absolutely. I like that comment. And Jared, you even put that in your talk. TJ asks, can you plant closely or allow other trees to compete, thinning, culling slowly over time to identify forest performance? I'm going to throw that to John.
Yes, I think you can. I mean, to some extent, we did that at Lesesne in the hybrid orchard. And actually, I say that shows you can achieve timber type even without the full American growth competitiveness if you manage the forest.
I've got a bunch of white pines planted amongst mine. I think the white pines will give them a run for their money.
Yes, and it helps them train. It helps train their form. Yes, so I think so.
Well, and that's interesting that y'all mentioned white pine. So Jared had mentioned the meeting that we were just at this past weekend, where Tom Clack actually gave another talk about finding the best site, and he said white pine, the best site of where he was planting up in Maine. That's my experience in seeing stuff in PA. They're closely associated, American chestnut and white pine in the natural environment. So I think there's something to that for sure. I'll take one more question. This is from Stephen Black. Why would people have selected for orchard form in the past? It's not like they have to pick the fruit. Seems like timber type form would be more valuable, plus the trees might grow more closely packed in an orchard, just challenging the assertion that orchard form was an intentionally cultivated trait.
It may not have been, but I think there is an advantage to it. If you're a nut producer, you want the nuts where you can get them pretty easily, and you also want large nut size. Also, which may be reversible, but I don't think we know. You look at some of the early reports of people that went to China and Japan, and I don't see a lot of evidence that they saw real tall trees. So it may be that it wasn't intentional, but I don't think we know.
I think it was. Bruce is on here. I hope Bruce is still on here. He spent a lot of time in China looking at Chinese chestnuts. I'll see what he knows. I mean, based on my limited experience there, I mean, I was there in September 2 different years, and lots of people were climbing trees and shaking the nuts out or picking them. So I mean, I think there was some intentionality there. And you're right, we have not seen a lot of timber form, but I think it's because it was so widely cultivated after centuries. That a lot of what was brought back in the early days was just what was easily accessible, and that's what had been selected. That's my assertion anyway.
And I would add, I think orchard form allows for a higher production of nuts per acre.
Yep.
Yeah.
I agree. Anonymous attendee asks, does the cost of genotyping continue to trend downward, or has it pretty well plateaued out? Jared.
Yeah, there's a lot of different methods to do this, but I think what we have is a very competitive for price. So yeah, it's like $18 a sample, and like other genotyping methods, it's still like 25 bucks or something. But one thing I like about the company we're working with is they do the DNA extraction. We can just send them a 96 well plate full of leaves, and they'll do everything and send us the data, and then we can do the downstream analysis. So that's like a key. But in terms of sequencing whole genomes and stuff, that's gone way down. We can sequence in a whole American chestnut genome for about $150. So that, compared to the billions of dollars that it took to sequence the human genome at first, that's just astounding.
Bruce says wild trees I saw in China are taller than orchard trees, but they don't look like Americans. And Frank makes a comment. We have Americans growing fine with no white pine, and I think that's a good point. Like, you don't need white pine and to have chestnuts to grow. It just means that they can. That's a sign of a good site, typically.
And I would say further south, it's more likely to be pitch pine or table mountain pine or other pines. Yeah.
Yeah, I think that there's a nice pine connection there for hardwoods in general too. Marcus Warwell asks, can an operational seed orchard with 30 or more clones having some resistant material that are 100% American from southern seed zones be established today?
I mean, the southern seed zones part is the challenging thing, Marcus. Dana from the Forest Service is working on grafting some of those. Dana's group, his tech, Chuck Burdine, is grafting some of those far southern source trees in Mississippi, and we're trying to get pollen off of those. And then, crossing those with wild type Americans that we have in orchards. But I think if you want to get the stuff today operationally, we certainly can do hybrids. We can get you these selected hybrids that are from our best hybrid parents that we've selected for majority American chestnut ancestry. So if the Forest Service wants to participate in that, we would love to have. We would be gladly give you some of this material to grow out.
Anita, last one. Anita, Jared, you spoke about linkage drag, but what is the burden of required outcrossing? Also, recombination is approximately 1 on either side of the centromere per generation. You are going to need lots and lots of trees, more than 300, to get the genetic combinations you want.
Yeah, we're thinking like for this recurrent genomic selection program, 18,000 genotyping, 18,000 and trees in that first generation. So that's, over the next few years. So that, yeah, we're trying to, and then we're going to continue to cycle through multiple generations and hopefully get good at the speed breeding and phenotyping growth, right? Like, we don't quite understand, if maybe there is major genes for apical dominance, for example, that we could be selecting for. I think figuring that out, it looks like that from some of the work that's been done recently is just showing like this apical dominance trait does seem to have some major genes involved in that. So if we can select for that and select for resistance, like, this linkage drag issue, we can take care of with multiple generations, but we need to be, like what Mike said, selecting for the traits we're interested in, and maybe we could worry less about the exact percentage American that we need.
Well, I think with that, we only went a few minutes over time. Mike, John, Jared, thank you guys so much for joining us today and presenting all that information. Kendra, thanks again for all of your prowess at Q&A. We're taking a month off. We're going to skip October. We'll come back in November with a topic to be determined. And join us in October in Connecticut, see way more of this stuff. Russell's coming to Connecticut. Awesome. That's fantastic. I know a few of you on this list are as well. Hope to see you guys next month in Connecticut. And until then, and until our next Chestnut Chat in November, take care and enjoy the fall. All right. Thanks, you guys.